So if we have a mixture of gases, two different gases or more, that makes a mixture. Air is a mixture of gases. Dalton's law applies to air. This makes it very convenient. When you have a mixture of gases, the total pressure is due to the sum of the what? Individual, the partial pressures. So, if the pressure due to molecule A is proportional to the number of moles of A, the pressure due to particle B is proportional to the number of moles of B. This means that the total pressure of this particular sample would be PA plus PB, and the mole fraction would be for A, NA over NA plus NB, and for B, of course, NB over NA plus NB. So this is how you get your mole fractions and your total pressure. If you rearrange this equation here, PA equals XA PT, this gives us the pressure of A in relationship to the total pressure. So once we know the mole fraction, we can use that to determine our partial pressures, and vice versa for P. So this is a generic equation. Generic equation here, PI equals XI PT. The I means some gas, whatever gas it is, as long as the I is the same thing for it.
What's that?
XI is the mole fraction. Mole fraction is the moles of that particular gas divided by the total moles in the sample. So to use this information here, if you remember this equation here, let's see if we can apply Dalton's law to a particular problem. So we've got a sample of natural gas. Contains 8.24 moles of methane, 0.421 moles of C2H6. What is C2H6 going to be? 2 carbons? F? Very good. And if it's all single bonds, it would be ethane. We would know that by the number of hydrogens. So, we got 0.116 moles of propane. If the total pressure of the gases is 1.37 atmosphere, what is the partial pressure of the propane? So, to solve for this partial pressure of the propane, you take the moles divided by the total moles multiplied by the total pressure. That's it. Here's your equation. Pressure total is 1.37. The X due to propane is 0.116 over the total moles in the sample, and that's it. That's all you got to do. So mole fraction, multiply those two together, you got your pressure due to propane, and that's it. Now let's consider this apparatus here. We have two gases, A and B. After the valve, this is representing two rigid containers. They're not flexible, they're not balloons, they stay the same size. There's a valve in between them. After the valve is opened, we want to determine the final partial pressure of each gas and the total pressure of the mixture. So with this information, it gives us pressure and it gives us what? Volume. Pressure and volume. So we've got pressure and volume. What's one thing it doesn't tell us about? Temperature. We can assume the temperature stays the same. So if we know pressure, we know volume, we know temperature stays the same. If we use Pivnert, we can solve for the number of moles. So once we get the number of moles in each, okay, so you have A. First we do it from A's point of view. When the valve is open, A spreads out to A and B. So when it's open, it spreads out to the entire sample. The new pressure, what would it be? So, if the volume is 3.2 liters initially, the pressure is 856 torrs initially. The new pressure is dependent on the volume. It's the volume of both of the spheres together. So 3.2 plus 4.8 equals 8 liters. If you use Boyle's law, P1 V1 equals P2 V2, you can find the pressure at the end. So one way we could have done it is gone through the mole, right? In this case, if we use Boyle's law, we can skip the mole to get the pressure due to the gas when it's mixed. So we just assume one point of view. We use Boyle's law. 856 torr is the pressure of A. 3.2 liters is the volume of A initially. and then the pressure of A at the end and the volume of A at the end. To solve for the partial pressure, this is called the partial pressure of A in the entire sample. So A gives up 342 torr, that's the pressure due to A. Then if we do the same thing for B, can it be as easy? Absolutely. Okay, we're just doing it from B's point of view. Boom, open the valve, B opens up. We've got the pressure, we got the volume initially. New pressure is what we're solving for. New volume is adding up the volumes, which is still 8 liters. We use Boyle's law and solve for the pressure due to B. So we got the pressure due to A plus the pressure due to B, and if you add them up, it'll be the what? Total pressure. So total pressure, boom, we got pressure of each. We found out the pressure of each, we just add them up. 473 plus the 342 is 815 torr. So this problem here, a lot of people look to go to moles on this. Okay, you could do it to moles, but then you're doing more what? More work than's needed. So when you look at something like this, okay, you can think of when you're dealing with pressure, sometimes you can just work through pressure and solve it. From A's point of view, then B's, then you put them together at the end. If we had 3 different gases, could we do the same thing? Absolutely. If we had 3, if we had 4, if we had 10, if we had 20, it would just take a little longer, right? Right? So when we collect gases, we do this in our magnesium lab. We put the gas through water, and it bubbles up here. There are 2 different gases here. So this is a partial pressure situation. There's pressure due to hydrogen, and there's pressure due to what? Water vapor. Now, the pressure due to water vapor is dependent on the temperature of the water you're using. So, the total pressure is the sum of the partial pressures. In this case, you got hydrogen and water. Should be a lowercase 2 and lowercase 2 there, as you know. That gives you the total pressure. If you wanted just the pressure due to the hydrogen, you would take the total pressure minus the pressure of the water. So, total pressure. The total pressure that's inside of here, when we line up the liquids, the total pressure that's inside of here is equal to what pressure? Atmospheric pressure, because the levels are the same. So the atmospheric pressure is our pressure total. The pressure due to the water, you would have to look it up on a table for temperatures of water. So you look that up, you got this, subtract the pressure due to the water, you get the pressure due to the hydrogen, and that will tell you the pressure of the hydrogen in the sample. Yep. The atmospheric pressure. Well, when you line up the liquid here and the liquid in here, I know they're not level right now, but when you did in the lab, what you did was there's pressure pushing down on this liquid here, there's pressure pushing down on the liquid here. When you line up the liquid levels, the pressure pushing down and the pressure pushing down is the same. So the pressure that's pushing down on the liquid here is due to the atmosphere pushing down on it. So the pressure inside of the container is the same as the pressure outside. Now, one way to recognize this, the pressure is going to be the same when the volume is not changing. So if the volume stays the same for 5 minutes, then we know the volume inside, the pressure inside is going to equal the pressure outside. If we don't keep the levels, if we don't keep the water levels equal, then we have a difference caused by water being pushed up in the tube, right? So if you moved the levels and they weren't level when you measured it, that would be a source of error that could adjust your again, pressure due to the measurements that you were making. So pressure total in this case, if we were doing it from our lab, was the atmospheric pressure. In this case here, do you notice the water levels aren't equal? We would have to adjust for that change, which would be a little harder to do. Now, adjusting for water, this here is a table you would look at. All you would have to do is find the temperature of the water. If the temperature was at 20 degrees, you'll notice the vapor pressure is 17.54 millimeters of mercury. When it goes up to 100 degrees, what value is this? Okay, 760. What's 760 millimeters of mercury? 1 atmosphere, very good. So the amount of pressure causing this is 1 atmosphere. So if it gets up to 100 and the pressure coming out of the water, pressure due to the water vapor, is equal to the pressure of the air. If that's true, the water no longer stays in the liquid phase, but it becomes completely a gas. So when they're equal, that's when the water can become a gas, or this is called the boiling point. At these lower temperatures here, does water evaporate faster at 65 than 20? Absolutely, because it is exerting more pressure pushing up into the atmosphere. Yes? This is for liquid water, yeah, vapor pressure. So it's the pressure of it going into the vapor phase at that temperature. So when it becomes a gas, it exerts this much pressure at this temperature. So if you had water at 100 degrees, the pressure inside above the water would be 760. So you're measuring the temperature of the actual water here, okay, to get the pressure that it's exerting. So usually the water temperature is what is exerting that that pressure. Yeah. No, you just look this up. So I think it says in the book there's a table. If not, you can use the internet or other thing. Yeah. No need to memorize this, but you should see what happens as the temperature goes up. What happens to the pressure? Goes up. Is it a linear relationship? No. Okay, you got an exponential relationship. Keeps going, until you reach this point. At this point, okay, it's all gas, so it behaves differently at that point. So it becomes all gas, so the pressure, you could continue to increase the pressure if possible. This is on page 485, table 10.8, so you don't memorize it. Yeah? Pressure of the vapor, yes. Yeah, so you measure the temperature from the water's point of view, but the water and the vapor, because they are both in the same container, will be at the same temperature. And that's due to thermal equilibrium. So that's why you can make that assumption. You could also measure, if you measure the temperature of the vapor inside of the container, that would be even better. But we don't have the thermometers to do that. Now, here would be a picture of a apparatus for measuring gas collection. On this apparatus here, if you had a chemical reaction here producing a gas, okay, in a test tube, it would be sealed off. The tube here goes into a container of water. This here is called, this here would be a bottle filled with water, just in case, again, just in case you needed to add more water into the system. And then you've also got a bottle full of oxygen gas plus water vapor here that will be collected. So as you collect it here, you can top it and put a new one on top and keep filling it up to collect more and more gas. This here is called the pneumatic trough. You made a pneumatic trough type device, even though we didn't have a tube. The pneumatic trough that you used was a single glass piece. So pneumatic troughs are commonly used because you take the sample, it goes underneath the water, and then into the bottle being filled with whatever gas it might be. Now, if we had oxygen gas being produced by the equation below, it's collected over water at 17.5 degrees Celsius. If the pressure inside the container is 772 millimeters of mercury, calculate the partial pressure of oxygen gas collected. So this was the equation we were looking at. The first thing we might have to do is look up what? Okay, the pressure due to the water. Because you're going to have what things as gases? You'll have what? Oxygen and what? And the water vapor. So if we go back and look at the water vapor, we were at what temperature? Okay, about 17.5. We got 15, we got 20. What do we do? Okay, all right, so let's see if we take the average for this. Okay, so 12.79, 17.54. When 17.5 is in between, you actually pick the higher temperature. So average makes sense, but you pick the higher temperature based on the data you have. So 17.54 would be the pressure due to the water, and that's proportional to 20 degrees. So the pressure here due to the water at 15.53. You set up a proportion here, 15.35 here. It should be about halfway in between the two, but they tell you to pick the higher one and then set up a proportion to find the pressure of the water. Then you can solve for the pressure of the oxygen. Maybe. There we go. All right. And you take your 772 minus your 15.35. So, if you chose to do halfway in between, that may get you close to the answer, but this here is the technique of proportions to get you the actual answer that would be used. So always use the higher number on the table. If it's 18, if this was 18, you would use the same ratio. Okay, so if this was 18, you'd use 17.54 to 20, P over 18. Okay, raise your hand if that makes sense? Easy? All right. So, 77 millimeters of mercury would be the pressure in that situation of the gas produced. This here is one application of the gas laws. In Carmel Valley, you can see some of these events all the time. The coolest hot air balloon ever, of course, is Darth Vader. Really cool. Yeah, I know. You guys might like other ones. All right, so at this time, I'm going to give you about 2 minutes break. Stand up and stretch if you need to. Write down this information if you need to. Okay. If you need to sit somewhere else, please do so right now. At this time, we're going to talk about kinetic molecular theory. We've learned about mixtures of gases. We've learned about the basic gas laws. Some things we know about gases are they are different from other forms of matter, not only by the power of their indefinite expansion so as to fill any vessel, however large, and by the great effect this has in dilating them, but also the uniformity and simplicity of the laws that regulate these changes. The laws are very simple and very clear for most parts of gases. This is written by James Clerk Maxwell, who invented an equation to show the motion of these gas particles. We saw the relationships as we took a gas. We decrease the volume, that's Boyle's law. Increase the temperature, that's Charles. Increase the amount, that's Avogadro's. And if we change the identity of the gas molecules, that applies to Dalton's law. Okay? The identity of gas molecules does not change the laws that are applied to them. There's only a few things that an identity of a gas molecule will change. It'll change density, it'll change mass, and it will also change what we're going to learn about with Graham's law next. Now, when we look at gases, some properties of gases we should be able to notice. Get this two up here. Load. Might work. Doesn't quite work the way it's supposed to. It's supposed to load right here. All right. So, not the fun animation. Let me see if I can find the not so fun one. It's supposed to happen like this? Yeah, no. No, it's actually a decent animation, but let's see if we can look at another one. This one is actually better and it always works, so let me open this up. All right, now, if we look over here, we have a person here. This person can change the volume of the container. Okay, we can also change the temperature by heating it up or cooling it down. Okay, and we can also change the amount of gas in here. So, in this case here, if we keep the temperature constant, you'll see as we add more molecules, what do you notice happening to the pressure as we add more molecules? Okay, increases. As we have a particular pressure, this is about 0.45 atm. If we change the volume, we decrease the volume, what's going to happen to the pressure? Pressure goes up. As we decrease the volume, what happens to the pressure? Okay, it goes down. Now you'll notice that something else is happening as we change this. Okay, the temperature has gone up, and then you have to cool it back down to get it back to its original temperature, which looks like it's around 300 Kelvin. Okay? So if you control the temperature, the volume and pressure are inversely proportional. If we keep the volume the same, and we increase the temperature, what happens to the pressure? Increases. So we know the relationship here. Now, there are some assumptions that we're making here. One assumption here is that these molecules are all moving, and they're all doing what with one another? Colliding. One of the assumptions is that these molecules, their volume doesn't affect the overall volume of the container. These molecules have a negligible amount of volume. As they collide with one another, though, the energy is completely transferred. This is a collision. Does anyone know what it's called when energy is completely transferred? Elastic. So it's assumed that the collision is completely elastic. The energy is completely transferred. However, you can see some of these molecules are moving at different speeds than others. The temperature is the same for the whole thing, 721 Kelvin. But are all the molecules moving at 721 Kelvin? No. Some of them are moving faster, some are moving slower. And we can see the relationship here by looking at what's called the energy histograms. You'll notice the speed of the molecules, the number of particles. There are some moving really slow and some moving really fast. But the majority is in this section here. This curve relationship that you can see here, constantly changing, this curved relationship here is what is called a Maxwell-Boltzmann distribution. It shows the mathematical relationship between the movement of gas particles and their average kinetic energy. The average is right about here, but you can see it's constantly fluctuating. And you see some that are moving really fast and some moving very, very slow, with the majority being in the middle. These properties of gases assumed a couple things. One thing that's assumed is volume of individual particles is 0. So their volume does not affect the overall volume. Now, is it true the volume of a gas particle is actually 0? No. So this is an assumption made for the kinetic molecular theory, and it works really well. Collisions of particles with container walls cause pressure. So the more they collide with the container walls, the more pressure you have. The particles exert no forces on each other. They do not attract or repel one another. And their average kinetic energy is proportional to the Kelvin temperature. So average kinetic energy is proportional to temperature, is how we can relate temperature to kinetic energy. Now, a gas that obeys all these postulates is called an ideal gas. So the ideal gas law applies and uses the kinetic molecular theory. Most gas laws use this theory as their basic guideline to begin with. Now, is it possible that some particles may exert forces on each other? Maybe. Is it possible that this is not true? Maybe it's not proportional. Maybe it is, maybe it's not at all conditions. Yes?
So kinetic energy is 1/2 mass times velocity, right?
Squared.
So it's proportional or similar to the temperature?
It is almost equal to the Kelvin temperature, but it's not exactly the same.
It's mass times velocity. Okay.
Yeah, so it depends on the mass, but the velocity as well. If you have a more massive particle, for example, okay, the mass of the velocity will be slightly lower than the ones that have less mass, but the total kinetic energy, the average kinetic energy of all the molecules will be proportional to the temperature. And the temperature is a measurement scale that we can use to measure all these particles.
Are
yep.
Joules equivalent to Kelvin?
They are proportional. Yeah, they're not equivalent, not exactly the same, but they're approximately equal to There's a relationship between the two. Now, the volume of individual particles is 0. So this means a gas is composed of molecules that are separated from each other by distances far greater than their own dimensions. So this assumption says the distance between the particles is so much greater than their volume that their volume is negligible, approximately equal to 0. Is it actually 0? No, but it is negligible. The molecules can be considered to be points, so they don't have an actual size to them. They possess mass but have negligible volume. The total volume of molecules is approximately equal to 0, and the volume of the gas equals approximately the volume of the what? Container they're in. So the particles aren't changing the volume we're dealing with. The volume of individual particles is 0. So if we drew a picture here, this shows the particles, these particles here. The volume of the gas is equal to the volume of the container minus the volume of the particles. So if the particles had volumes that was measured, the kinetic molecular theory says, no, the volume of the gas is equal to the volume of the container. That means the particles are negligible. They don't contribute to the overall calculation. Now, why is that? Well, the volume of the particles is incredibly small. It's so small that when you take the volume of the container of 200 milliliters and you subtract 0.0000000.5, 0.0000005 milliliters, does that change the volume overall? No, it's negligible. It doesn't change it enough to be considered. So when you're dealing with most gases, kinetic molecular theory works well for that. Yes? Correct. The particles are the gas, so you assume that these particles are of negligible volume, and the gas occupies the entire container. It fills the container. So that's one assumption about gases, they fill the entire container. So here we just assume that the volume of the actual particles isn't big enough to affect the volume of the entire sample, which is called the gas. Now, the collision of the particles with the container of the walls cause pressure. Gases are in constant motion and they move in random directions. So the motion of the molecule is random. It is not something that is predictable. However, as they collide randomly, they move throughout the sample. So if you saw a single gas molecule moving throughout this square, you could see its path is not predictable because of the collisions with the container and with other individual molecules. They frequently collide with one another, and their speed changes, their velocity changes, their momentum changes. Collisions among molecules are perfectly elastic, is our assumption. The particles also exert no forces on one another. So if you have gas molecules exert neither attractive nor repulsive forces on one another, the particles do not have intermolecular forces. They do not have any intermolecular forces is the assumption by the kinetic molecular theory. So, in reality, one particle may be attracted to another because of its polarity or because of its properties. In the kinetic molecular theory, these particles move constantly, but they are not assumed to attract one another at all. What's meant by the average kinetic energy, as we talked about, any two gases at the same temperature will have the same average kinetic energy. So the kinetic energy per molecule is equal to 1/2 mv squared. So that's our kinetic energy equation. The kinetic energy per mole is 3/2 RT. So we use our ideal gas law constant to determine the kinetic energy per mole. These two equations, both would be ones you want to be able to use as necessary for the energy of molecules and moles. Yep.
Was that V, do we use like an RMS speed or?
Yes, you would be using that. So we'll look at this about right next. Yes, this would be the velocity value. If you're given the actual velocity of the molecule, the mass of the molecule, you could calculate the kinetic energy per molecule. Usually you're dealing with this equation here in chemistry because you want an amount, and you usually never have one molecule by itself, but you could calculate that as well. Now, Kelvin Temperature is an index of the random motion of the gas particles. So it is an average related to the kinetic energy. So the higher the temperature means the greater the motion is the basics behind the Kelvin system. If we go down to 0 Kelvin, then we would have zero motion if we could go down that low to absolute zero. So if you look here at this simulation, this is a gas moving at a particular temperature. Okay. If we modify the gas and cool it down, okay, and we cool it down, what do you notice about the molecules? Okay, all right, they decrease their speed. Now, what else do you notice about the molecules right now? There's no collisions. Okay? They're moving through each other. So all of these molecules here are moving with the same velocity. The same velocity. Okay? And they're not colliding at all. How come? It's the way the simulation is set up. Does this actually happen? Nope. They're always colliding with each other, and we have to think of not 2 dimensions, but 3 dimensions. So sometimes it's possible for a molecule to travel and not collide with any other molecules until it hits the side of a container. Let's see if we can show you. And then hot gas. Now, so this is just velocity. Low velocity, high velocity, low velocity. All right. So that relates just Kelvin and kinetic energy. Again, they don't all travel at the same speed. Be nice if they did. Yeah.
Wouldn't that technically be better named ideal gas? I mean, ideal gas.
What, kinetic molecular theory? Yes, a better theory. Ideal gas fits the kinetic molecular theory. Now, to sum up what we know about KMT, kinetic molecular theory, particles occupy a small part of the total volume. The particles move rapidly and they collide constantly, which we didn't see in the last simulation, of course. Little mutual attraction or repulsion between particles, and collisions cause change in the direction and the velocity. And that can be predicted based on the collisions that are made. Now, this is for kinetic molecular theory. It works for an ideal gas. When you compress a gas, you can use the kinetic molecular theory. When you use Boyle's law, you can use the kinetic molecular theory. The pressure, the collision rate with the wall will tell you the approximate pressure. The collision rate is proportional to the number density, how many molecules per unit volume. The number density is proportional to 1 over the volume. It's inversely proportional. So that means pressure is proportional to the inverse of the volume. Number density is proportional to collision rate. Collision rate is proportional to pressure. And this tells us that pressure is proportional to 1 over V, or the inverse of volume. With Charles's law, the pressure is equal to the collision rate with the wall according to kinetic molecular theory. The collision rate approximately equals the average kinetic energy of the gas molecules. And the average kinetic energy is proportional to the temperature. So therefore, pressure is proportional to temperature, and that is Charles's law. So using the kinetic molecular theory to prove a law means we have to go through these steps. Collisions. Then collisions, number density, 1 over V. Collisions. Collision rate is average kinetic energy. Average kinetic energy is proportional to temperature. Pressure and temperature are proportional. So we used the laws, and then we got to the KMT. You could go backwards through it. Same way. What if you apply it to Avogadro's law? Pressure is still equal to what? Collisions with the wall. Now, what are collisions with the wall going to be proportional to for Avogadro? Somehow we got to get the moles. Collision rate is proportional to the number density. the number of particles per unit volume. Number N over V. Number density is proportional to N by a factor of V, of course. So it's relationships. What about Dalton's law of partial pressure? Pressure is proportional to what? Amount of moles. Molecules do not attract to one another. So if you have different gases, they don't attract one another. They don't stick together. So it wouldn't change the molecules. The pressure exerted by one type of gas molecule is unaffected by the presence of another gas. So if you got hydrogen, helium, nitrogen, oxygen all mixed together, they do not affect one another in the Dalton's law of partial pressure due to the kinetic molecular theory. So the pressure total is equal to the sum of the partial pressures. Now, if we're trying to study the speed at which molecules move, this here is an apparatus. Okay, heating up a sample of gas. As the sample of gas goes through, there is a chopper with a rotating slit that allows the gas molecules to move through here. Then it's able to detect these molecules. As this object is, again, continuously spinning, you can get a distribution of the slow molecules versus the fast molecules. The fast molecules would land here first. Average molecules is in the middle, and you can see there are less slow ones and less fast ones than our average. And this gives us an average speed of the molecules in a particular gas sample. So you put the gas sample in here, heat it up, measure that sample as it passes through these two rotating slits, one being a slit, one being a detector. As we saw earlier, this here is what is called the Maxwell speed distribution. You can see here the molecules that are sorted by speed. There are quite a few that are average in this range. There's very few that are slow. There's quite a bit that are moving faster than average, and very few that are moving extremely faster than average. This distribution shows that the average kinetic energy would be somewhere right there. However, it's not a bell-shaped distribution. More molecules are on the slower side of things here than on the faster side of things, if we were looking at it in that proportion. There are many different molecular speeds, and if you did this experimentally, if we watched gases moving in a simulation, you could actually count how fast a gas particle is moving, and we could sum this up as well. This was invented by two different people, James Clerk Maxwell and Ludwig Boltzmann. And it's called the Maxwell-Boltzmann Distribution of the kinetic energy. There's debate on that, but they invented it at the same time. Maxwell usually gets more credit than Boltzmann for it, but it's named for both of them because of the work they did. Maxwell's a little bit had the ideas, and then Boltzmann implemented it into a mathematical equation. So the mathematical equation portion, there's a little more work here done by Boltzmann. Yeah.
Is that why Boltzmann got his name for a function on Maxwell?
I think so. But they both did some great work, and this relationship is something that you should be familiar with seeing, and also be familiar with the motion of the particles. Now, if we look at nitrogen gas, this is one thing that's unique about the Maxwell-Boltzmann distribution. As you increase the temperature is the average kinetic energy. So the temperature of this is 100 Kelvin. Temperature of that is 300. Temperature of that is 700. What do you notice happens to the distribution? Okay. Flattens out. Are there still molecules that are moving incredibly slow in both cases? Yeah. Are there still molecules that are moving faster? Yeah, these are moving much faster, and so on. So it just flattens it out and distributes it so that there are more moving faster, and the average increases. The average is approximately where the peak of each of these curves is at. So the average is just the temperature we're measuring. So when you stick a thermometer in, it says 27.2 degrees Celsius. You convert that to Kelvin. That's our average, whatever it might be. The distribution of the molecules, not all molecules are moving with average speed. If they did, they wouldn't be able to collide like we saw in that simulation. Now, the interesting thing is, look at this. All three of these are at the same temperature. Huh. Different gases move different things because 1/2 mv squared. As you increase the mass, what has to happen to the v squared? V's got to go down. The kinetic energy to stay constant. So if these are all the same kinetic energy, the heavier gas has its average much closer, and then the lighter gas has its average much higher in terms of the molecular speed. This is molecular speed here. Now, you'll notice these two graphs look similar because kinetic energy depends on mass and velocity. Now, question.
Does that mean lighter gases get hot faster?
Lighter gases get hot faster. That would seem to make sense to me. Okay? That is a great synthesis of that information. It would make sense. Yeah.
So the masses of different gases are different, but what was it that was close to zero?
Volume.
Oh, volume.
Yeah, volume is negligible. So chlorine gas and helium gas, they actually have different sizes, but both of their sizes are small compared to the total size of a container, that it's negligible. So close to zero.
So volume is almost, most of them are all the same volume, but the masses are different.
Right. Right. Volume can be assumed to be zero for almost every situation. Unless you're dealing with incredibly small ones. Now, some important things you need to pay attention to. Caution information. With Maxwell-Boltzmann distribution, some of you talked about the Joule. How does the Joule fit in with this? Well, Mr. James Joule. Yeah, Mr. James Joule, he actually did a lot of experiments with energy and energy transfer. Some really cool experiments that were done using a water wheel. Joule is the unit for energy. Okay, even though we use a lot of Kelvin in here, Kelvin is the measurement of temperature. Joule is the measurement of energy. Temperature and energy are not the same thing. Energy is the capacity to do work. So, if I was standing over here, and there was a device, electronic device here, I could ask a student, can you lift this over your head?
You can't. Sorry.
No, he can't do it, but he had the energy to shake his head. That movement is considered work. When you apply a force over a distance, that is considered work. If you put your hand out like this, you hold your hand out here, what happens after a while? You get tired. But are you moving your hand? No, there's no displacement whatsoever.
Oh, wait.
Yeah. So are you really doing the work?
No. Well,
Yeah. Okay, you're working against gravity.
wait, currently though, but currently, whoa, it's not work. It's work plus displacement.
Yeah. Yeah, based on our physics definition, work is force over a distance, or force times displacement, depending on your preferred language. But if you hold this here and continue to hold this here for a very long time, you get tired. It's like climbing a bunch of stairs, you get tired. When climbing stairs, you know you're moving. But here you're like, wait a minute, I'm not doing much. Your hand starts to get really heavy. And your muscles start to hurt. Inside of here, is there movement going on? Yeah, there's lots of things going on. Your muscles actually are moving back and forth, back and forth, and back and forth. Every time they displace, they're doing work. You need energy in order to do that. And we know we can get energy from carbohydrates. Yeah. So some of you, I know some of you, you're sitting here, you're pretending to look like you're not paying attention at all. Okay? But you're actually doing work just sitting up. You may not even think that. Now, when you sit up, your body wakes up. When you lay down, your body goes to sleep. So, please don't lay down in class. Now, the cool thing about joules. A joule is called a nucleon. Alright, the peanut gallery over here. Alright, now, it's 1 kilogram per meter times meter squared over second squared. Joules are a measurement of the mass in kilograms times the velocity squared, meters per second. So if the mass is in kilograms, that equals a joule. If the mass is in something different, then it equals part of a joule. So if the mass is in kilograms, the velocity is in meters per second, and R is 8.31 joules per mole per Kelvin. So these here are equations for kinetic energy of molecules. These we will need to be able to use and know how to use. When you think of it.
I have a question, but I don't know how to say it.
Now, one thing you'll notice is kinetic energy is in joules. M is mass, that's kilograms. Velocity squared is meters per second, and you square both of them. So that's why a joule is a unit of energy, and why both of these equations will give you the correct units.
So, R is supposed to be...
Joules per mole Kelvin.
So we have 8.1 moles.
It's going to give you joules per mole. That means it goes on the bottom. The inverse, joules per mole.
Okay, so really it's 8.1 joules over moles.
Moles Kelvin. Oh no, we got a double star. All right. If you didn't remember this yet, please take out your phone and take a picture of it. Now, earlier on we were talking about RMS. Okay? So, molecular speed, how to determine a molecule speed. You take 3 kT over m, take the square root of that, or 3 RT over m, R being the ideal gas constant. URMS stands for the root mean squared speed, or root mean squared velocity. What's up? I'm not going to ask that question right now. Now, Boltzmann constant is the K in this equation. This enables us to determine what's called the root mean squared speed of a molecule. If we know the mass of it, temperature, and K, we can plug it in here to get the root mean squared. Yep. This is the capital M, this is the lowercase m, this stands for mass. I believe that capital M, I'm assuming, will be molar mass. Even though it's not a should be a funky M. I'm sorry, it's not funky. Yeah, regular M. Small m means mass in kilograms. Big M is molarity. Funky M is molar mass. Yeah. Yeah, it looks the same here. It's supposed to be italicized. Right? Hey, if it's up to me, I put this as MM. But that's just me. Yeah. That is the speed of a single individual molecule. Because you have to take the average of all of the different velocities that the molecule is moving. you will take the square root of this information to get that value again. So there is a square in it. All right. All right, let's see if the next simulation works. All right, so if we look here at a gas simulation, we can get this to work, simulator. You want to follow one molecule? So, as you watch the gas, this is a gas that is actually moving. You can calculate the collisions per wall and the root mean square velocity. Right now, you can follow this molecule here. Turn it around. Now you've got all of these. The distribution looks like Maxwell-Boltzmann distribution here. This being 0, this being 12.662. Some things we could change with this. Number of atoms. You double the number of atoms. You can still see the distribution is the same. We have more atoms. The root mean square velocity is still 4.221. Let's change the mass of the atom. It's 28 now, which is approximately nitrogen. Let's change it to 32, which is oxygen. O2. So if we change it to oxygen, you'll notice right here the root mean square velocity changes. It goes down, 3.942. What if we change it to chlorine? Start it again. What's going to happen to the root mean square velocity of chlorine? Goes down. What if we change something else about it? Temperature, 600 Kelvin. Still chlorine. Start it. Yeah, the velocity went up. The root mean square velocity goes up as the temperature goes up. It also goes up as the molar mass goes down, and down as the molar mass goes up. So if we change this here, another gas, helium. Oh, I changed the number of atoms. So there's 50 heliums. You'll see their root mean square velocity is much higher. So what's the advantage of the root mean square velocity? Is it tells us speed of individual molecules. It also depends on the mass and their velocity. Okay, their mass and the temperature. Now, one thing that happens, you guys started to learn about this with the absolute zero video. One of the things that happens is when a particle reaches a very low temperature. This is 1.7 times 10 to the negative 7th Kelvin. No more work. Stop doing work. Put your hands down. Alright. You can do lots of work. You don't need to put your hands up though. You'll notice here, this here is the fifth state of matter. First one being solid, liquids, gas. If you increase the gas to a high enough temperature, it becomes a plasma. Plasmas can be redirected by using a magnetic field, so you can move a plasma. If you go the opposite direction, the super cold atoms. Okay, it's called a Bose-Einstein condensate. And here you can see the relationship between the electrons as you reach very low temperatures. Okay, it reacts and interacts differently than the matter around it. So this is a distribution, a velocity distribution of rubidium. So here you can see these are moving fast, much faster and much faster here. Yeah. Usually you can't exist very long because depending on what environment it's in. But you can't keep it at a low temperature very long because the whole environment, whatever environment you're dealing with, is at a high temperature. So it's hard to get this to this low temperature. Yep. Yes, it is. All right, ladies and gentlemen. Okay, we will be doing another lab tomorrow probably. On Monday, lab 6, 6B, and 27. You want to make sure you have all those with you. At this time. Gas light PS1. Yeah, it is online. Yeah. Oh, there it is. What was it? All right. So, talking about graham crackers. All right. Molecules. Kinetic molecular theory tells us this. However, this is only true if all of the kinetic molecular theory parameters are in place. Okay? So, random motion, constant temperature, above 0 Kelvin, of course. High concentration equals a high collision rate. So the closer the molecules are together, the more they're going to collide. Further, the more space, the less number, density, the less collisions. After the collisions, the particles end up in directions away from the area of high concentration. They want to go from a high concentration area to a low concentration area in molecules movement. When gases diffuse, they also have the same property. They are in a small area to begin with, and they spread out to occupy the area of the particular space. Okay? Diffusion of gases, also called whoever smelt it dealt it, because if somebody in that side of the room smells really bad, the first person to know will be the person next to them. Or if they smell really good, they used too much cologne today, and you go, the people over here will smell it first, and it will slowly spread throughout the room. What's trying to happen is the high concentration of particles is trying to spread out to equilibrate the entire concentration. So it's equal throughout the entire room. Okay? Now, this is a gradual mixing of molecules. It happens because of the kinetic properties of the molecules themselves and how they move. It always proceeds from areas of high concentration to area of low concentration. High pressure to low pressure. High concentration to low concentration. Temperature also does the same thing. High temperature to low temperature. Almost everything goes on this gradient. This is called a concentration gradient. You always want to equal out that concentration gradient if possible. In this case here, the rate of diffusion is proportional to the distance traveled by gas 1 divided by the distance traveled by gas 2. this is equal to the square root of the molar mass of 2 divided by the square root of the molar mass of 1. So if you have a container with hydrochloric acid and ammonia, hydrochloric acid vaporizes into HCl. This is actually ammonia hydroxide, vaporizes into ammonia. And as the molecules move, they come in contact with one another and they form a solid ammonium chloride. This solid forms a white ring right on this tube. We could actually do this with, if we had concentrated ammonium and hydrochloric acid, we could do this with a straw very easily. What happens is, where the white ring occurs depends on which one moves faster. So which one of these two do you think moves faster, the NH3 or the HCl? NH3. Now the reason it moves faster, okay, is proportional to, again, the distance traveled by gas 1 is proportional to the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. Yes, sir? That would be a cool lab to do, huh? There are many labs that we can do with gases. We've chosen a few of them. This one is not one that we've chosen because of the concentrated hydrochloric acid and the ammonia. But I'm going to see if I can get it set up for you guys. It takes about 20 minutes. It's pretty easy to do. You could do it while you're doing another lab. So if you're interested, we could look at how this occurs. And it's really pretty awesome because the equation, if you look at this, this is ammonium hydroxide. This is hydrochloric acid. Where do you see the white precipitate in the middle of the air? It's over here. It's closer to this. That means that this is moving faster than this is moving out. And you see that white precipitate of ammonium chloride forming right up here. What's up? Yes. It should fall to the ground. If it is heavy enough, it will not be suspended very long in the air. Yep. Absolutely, it's evaporating that fast.
So yesterday,
Yes.
and it was evaporating.
Yeah, not as fast. Yeah. So this is about, well, I don't know the molarity on that exactly, but it's usually about 18 molar. It's concentrated. This is about 18 molar as well. When you open this up, like when I made this solution for you yesterday, I used concentrated hydrochloric acid. When I opened it up, it immediately vaporizes. You can see actually it reacting with some of the things in the air. You can see the fumes. If you breathe them in, you could be in really trouble. So you should do it in a fume break. Yeah.
Maybe this is a dumb question.
No.
But I thought you said that ammonium hydroxide decomposes.
Very good. It does.
So how do you have it in a bottle?
It decomposes into what two things? Water and ammonia. So when you close the top of it, the ammonia becomes a gas here, right? So the ammonia is gas here. So when you seal the top of it, the pressure inside increases. The pressure inside increases, so it does not allow the ammonium hydroxide to vaporize anymore. So the pressure of the ammonia actually keeps it as ammonium hydroxide. So if this was an open container like this, the ammonium hydroxide does decompose into ammonia, which is a gas, which goes over here and reacts with chlorine. If you left it open for long enough, you just have a bottle of water. And this is why, do I have, I think I have one here. Could you drink it? Yeah, but the problem is this. Yeah, how do you know all the ammonia's out? Good question. How do you know it's all out? Yeah. So, one way of testing this. Mom's here? Just breathe.
Man, I'm dying!
Alright, so we have one down. Who wants to be next?
I volunteer.
You're not breathing.
I'm gonna just.
Yeah. So this is funny because this is called ammonia. But ammonia is a gas. Right? So this is actually ammonium hydroxide in here. Because it's cheap, alright? Chen is exactly right. The experiment I just showed you, okay, the way it's set up actually is to work with ammonium hydroxide. And what people do is they actually calculate the value, and you say, instead of this being ammonia, you say it's NH4OH. Is that going to give you the wrong molar mass here? Yeah. So you could actually calculate this out, and you're going to get the wrong molar masses if you used ammonium hydroxide. So we learned that from our reaction predictions. You told me it's always ammonia and water. How's it possible that it's ammonium hydroxide? Well, it's actually a situation where it's at an equilibrium situation. Yes?
But the M stands for molar mass?
Molar mass, yes.
Oh, okay.
Yeah, this M stands for molar mass.
But then, isn't molar mass
Molar mass is,
molar mass is big M?
it's a funky M. Yeah, it looks kind of like this.
And isn't molarity M mass?
Yeah, molarity is this. Just capital M is moles per liter. N equals moles. And then kind of italicized M equals molar mass. So if you see a capital M, sometimes you gotta figure out. I tried to italicize these to show it, but it's not great. Now, this relationship here, NH3 is 17 grams per mole, HCl is 36 grams per mole. So, which one moves faster, the one with the higher molar mass or the lower molar mass? The lower molar mass. So, the lower molar mass, the molecules are moving faster because of the mass-velocity relationship. So, the diffusion of gases does depend on their mass. The identity of the gas does determine the diffusion. The identity of the gas doesn't matter for the ideal gas law, but it does determine diffusion rates. Yep. Question? Now, effusion is a little bit different. Sounds like diffusion, but it's got an eth in it. Effusion describes the passage of gas into an evacuated chamber. So if you have a gas in here, and you have a valve here, and then you open it up, and this is completely empty. A vacuum, completely empty, no particles whatsoever. It's the rate at which those molecules travel into the second container. So a gas under pressure escapes from one compartment of a container by passing through a small opening. Usually it's called a pinhole into the vacuum side. You control the environment, the temperature of it. No air in the apparatus. Gas particles only collide with walls and each other. Therefore, measuring diffusion rate is much more accurate than the diffusion rate. So for diffusion, the challenge in that is you already have air in there, right? And so the speed at which they move is dependent on the air they collide with. And if the air has water molecules in it, that adds to the amount of molecules you have in that sample. So how would this look? Let's say we had a sample of hydrogen gas. Number of molecules here. See if I can get this started. There we go. So at this time you can see you have 18 molecules on the right, 1 molecule, 2, 3 molecules on the left. So 14 and 5, 6 and 14. All right, we close it up. We've got 13 on the right and 6 on the left. 13 and 6 for hydrogen. Now let's do it with oxygen.
Why don't they collide together?
Because it's a simulation done by Iowa State.
So Iowa State
they decided not to go with all the different velocities and how they can change. It's easier just to do an average speed.
Oh, that's
All right, it says 5, but there's 6. We know it's off by a little bit. But you can see that the all right. So let's put this into Graham's law and stop making fun of the computer programmers who probably are just chemists trying to do a simulation. All right. Thomas Graham, whose Graham's law of effusion is named after, saw that the rate of effusion is equal to the square root of the molar masses of the gases, the inverse of those molar masses. So the speed at which something effuses is proportional to the molar mass, but it is an inverse relationship between these substances. So R1 would be gas 1, R2 would be gas number 2. The rate is in volumes per unit time or distance per unit time. So it could be volumes if you're dealing with larger amounts, or distance if you're dealing usually with smaller amounts. Yep.
For the diffusion one, what was that rate measured? Volume over time as well? A while back you gave us the difference.
I believe it's the same. Yeah.
I thought, diffusion rate and diffusion rate should be similar either, but then.
Yeah, the only difference you'll see is the square root here goes over the whole thing, and in diffusion it goes over the M2 and M1 individually. Yeah, so it is very similar, but mathematically there's a difference. So effusion is a little, what's up? Just look at the square root. Different gases, different gases. All right. All right, when you calculate the answer to this problem, this will be your ticket out. So come up with the answer to this problem, bring it up here. If it's correct, you're good to go. For an unknown gas. There we go, is your equation, just in case you forgot it.